Last time, we found that our direct view of the early universe is blocked by the hordes of free electrons which existed prior to the formation of the first atoms 380,000 years after the Big Bang. With only 1/2000th the mass of a proton they consort with, they are now moving 45 times faster, that's the square root of 2000, than the protons, and they intercept photons of light at every turn, scattering them hither and yon, obscuring a clear view to the beginning of time. This is because the universe is just too hot, and thus the photons too energetic to allow the protons to capture the electrons into stately orbits and get them out of the way. So we cannot see directly farther back into the past than 13.7196 out of the 13.7200 billion years since the universe was born. That's still pretty good, but it's not all the way and won't allow us to fulfill our promise to measure things back to the beginning of the constituents of atoms. As the 17th century French mathematician and philosopher Blaise Pascal said in another context, quote, "If our vision be arrested here, let our imaginations pass beyond." In our case, our imagination is highly constrained by the host of observations that allow us to construct a precise model of the universe's birth. Running the clock backwards from the 380,000 year mark, the last thing we can see, the universe continues to get smaller and hotter and denser. Smaller, because we're going backwards in time, the space-time is shrinking. Hotter, because as that space-time shrinks, the photons that are waving through it have their peaks compressed, and shorter wavelengths means hotter temperatures. And denser, because the number of particles in the universe remains constant for a long time, and as you squeeze the space with the same number of particles, it just is denser. As we continue our journey to the beginning, we will pass through first the radiation era, where photons rule, and then successively through the lepton era, the hadron era, and the quark era, where these particles, our trusted historians, had their birth. There are a few physical processes which it is important to review before we embark on this journey to the beginning of time. Number one, mass and energy are interconvertible. Photons with sufficient energy can spontaneously create particle-antiparticle pairs. Never only a particle or an antiparticle, but particle-antiparticle pairs. And whenever a particle meets an antiparticle, the two come together and annihilate, usually into a massless photon. The equivalence is given by Einstein's famous equation with just a little twist. E equals 2mc squared, where c squared is the velocity of light, and m is the mass of one of the particles. The 2 is because we always create a particle-antiparticle pair. The second important physical principle is that a photon's energy is inversely proportional to its wavelength. That is, short wavelengths means high energy, long wavelengths mean low energy. As space-time expands, the photons traveling through it are stretched to longer wavelengths and thus lose energy. Putting these two concepts together, we can introduce the idea of freeze-out. When photons are energetic enough, they freely exchange places with particles. Photon goes to, for example, a proton plus an antiproton, and a proton and an antiproton come together to make a photon. This goes on time after time after time. In the ever-expanding universe, however, a moment will come when the photon energies fall below the threshold they need for creating a particular particle-antiparticle pair. The particle-antiparticle pairs around at that time can still annihilate and make photons. But when they make that photon, the universe then stretches a little bit, the peaks of the waves of the photon get a little farther apart, they lose energy, and they can no longer reconvert to particles. Any particle stuck without an antiparticle mate will be left in that state forever. It's sort of an extreme form of musical chairs. And every photon in that state is doomed, likewise, to travel at the speed of light through space for eternity. The freeze-out temperature is different for particles of different masses. Protons obviously require more energetic photons to produce them than do electrons because their masses are nearly 2,000 times greater. These different freeze-out points for the different kinds of particles we make are the demarcation lines between the eras of the early universe. So, Starting at 300,000 years, the last thing we can see, the conditions are very well established by the characteristic of the cosmic microwave background. The temperature is 3,000 degrees Kelvin. Tiny fluctuations around that value are present and reflect small energy fluctuations from much, much earlier times. As the universe evolves, these tiny inhomogeneities in the background grow through gravitational interactions to become massive galaxies. But for now, at this point, the matter and photons are really very smoothly distributed throughout space. There are about 1,250 protons and electrons in every cubic centimeter of space. Every sugar cube has over 1,000 protons and electrons, roughly the density of star-forming clouds in interstellar space today, the places where the sun and other stars form. The whole universe, however, is filled to that density. There are roughly 1 billion photons for every proton. This is a consequence of events that occurred at the very earliest times, which we'll explore shortly. The number of protons and electrons and the number of photons has been roughly constant from then until now, 380,000 years in. The only difference is that the photons have cooled because the space has stretched so much and the particles have spread out with the billion-fold expansion of the universe. Indeed, running the clock all the way back to when the universe is just 3 minutes old, from 380,000 years to 3 minutes, virtually nothing changes, except that the temperature rises as, in our backwards running clock, the universe shrinks and the peaks of the wavelengths come together, and the density increases as we pack the same number of particles into a smaller and smaller space. Between an age of 3 minutes and 1 second, however, there's lots of action. At t equals 1 second, 1 second after the birth of space, time, matter, and energy in the Big Bang, the temperature of the universe is 10 billion degrees Kelvin. And the density of matter is 1/10 of that of water everywhere, the entire universe, 1/10 the density of water. That's the matter. The radiation, compressed into this tiny space with their wavelengths all shrunk, is 1,000,000 times more energy than the matter. It's 1/10 of a ton per teaspoonful. That's me in a teaspoonful, like that. This is the radiation era. The dominant forms of mass and energy, or mass energy, remember, mass and energy are equivalent, so keeping track of the total is sufficient. The dominant species at this time is the photon. When this era begins, there are 2 neutrons for every 10 protons, because of earlier conditions that we'll explore in a minute. The neutrons and the protons in this era readily collide with each other and they stick to make deuterium, heavy hydrogen, 1 proton plus 1 neutron. However, the photons at this temperature, when the universe is 1 second old, are energetic enough to split those deuterium atoms apart again. The binding energy of deuterium, the amount of energy given off when a proton and a neutron comes together, as we saw in the cycle that powers the sun, is about 2.2 million electron volts. That's how tightly they're bound. That's how much energy I must add if I want to see them split apart again. But at a temperature of 10 billion degrees, the energy of the individual photons is 4.3 million electron volts. So they have plenty of energy to knock apart any proton-neutron pair they come across. Thus, while deuterium forms, it's immediately split apart by the billion photons that exist for every one of the matter particles. Simultaneously, neutrons decay. When a neutron is bound up in the nucleus of an atom, it can be stable for the life of the universe. But a neutron sitting alone on a table has a half-life. It's radioactive, if you will. That's 10.3 minutes. On average, a neutron will fall apart every 10.3 minutes. A collection of neutrons, half will disappear in 10.3 minutes. And so in the first couple minutes of the universe, the free neutrons running around, the ones that either failed to join with a proton to make deuterium or got knocked apart again by one of these overambitious photons, those neutrons are decaying, disappearing, spitting out an electron to turn the neutron into a proton. Thus, After 90 seconds or so, there are only 2 neutrons for every 14 protons, as opposed to 2 neutrons for every 10 protons when we started the era at 1 second. And with the expanding universe rapidly stretching the photon wavelengths, the temperature has fallen enough that the photons can no longer split deuterium. So we have fewer neutrons around because some of them have decayed, but all that exist quickly join with protons because that reaction is very much favored, and photons can no longer split them. That leaves us with 12 protons and 2 deuterium nuclei for every 16 original particles. Again, the 2 key features are neutron decay and deuterium formation. Deuterium nuclei are highly reactive, and at these temperatures they quickly bind together, 2 deuteriums, to form helium-4. After 3 minutes, it's all over. We're left with roughly 1 helium-4 nucleus for every 12 protons. 4 particles over a 16 total is about the observed 22% of the primordial mass that we said before is in helium. In addition, a few of the deuterons, a few of the deuterium nuclei, meet up with a single proton and make helium-3, or combine together in a more complicated way to make one of the 2 isotopes of lithium. Those 6 components, hydrogen, deuterium, light helium, heavy helium, lithium-6, and lithium-7, were the 6 primordial elements we discussed last time. Now, the exact amount of helium-4 produced is very sensitive, both to the temperature during this time and to the initial proton-to-neutron ratio. Likewise, the amount of deuterium left over, the 30 nuclei out of every million that we found last time by measuring the light from distant black holes shining through the clouds of gas in between us and them, is very sensitive to the density of the matter at this epoch. So we have proton-photon ratio, we have temperature, and we have matter, all constrained by the measurements of these primordial isotopes. Thus, these observational constraints on abundances give us considerable confidence that we understand what was happening during this key time between 1 second and 3 minutes into the universe's life. Now, to discover why the initial proton-to-neutron ratio was 10:2, we need to go back beyond the radiation era to the lepton era, to the time between 1/10,000th of a second and 1 second after the Big Bang. I know this is starting to sound a little absurd, that we can hope to understand what was going on at 10,000th of a second after the beginning of the universe, but follow the story. It hangs together. In this era, we began with a temperature of about 1 trillion degrees, and the matter density, just the matter alone, was the 10th of a ton per cubic centimeter, me in a teaspoon again. Because of yet earlier conditions, there were 1 billion each of photons, electrons, positrons, neutrinos, and antineutrinos for every single proton. 1 billion to 1 for each of those fundamental subatomic particles. Neutrons combined with positrons to make protons. A neutral particle, add a plus sign, you get a proton. And protons combine with electrons to make neutrons. A positive proton plus a negative electron makes a neutral particle. So this went on willy-nilly. Remember, there was only 1 proton for every billion electrons, so there were plenty to join up with. There was only 1 proton for every billion positrons, 1 neutron for every billion positrons, so there were plenty of positrons to join up with. This went back and forth over this entire period of a 10,000th of a second to 1 second. Now, since the neutron is 0.5% heavier than the proton, just slightly heavier, it takes slightly more energy to create it. Near the end of this era, the freeze-out idea comes in. This small energy difference becomes crucial, and we end up with 5 times as many protons as neutrons, or this initial proton-neutron ratio of 10:2. Now, to discover where these protons and neutrons came from, however, we have to go a step further back, to the hadron era, in which the baryons are produced. Those of you with a good memory will recall from Lecture 2 that baryons are triplets of quarks. The common triplets we know, protons and neutrons. At 2 trillion degrees Kelvin, photons have enough energy to spontaneously produce a proton-antiproton pair. The energy of the photon at 2 trillion degrees is about 2 billion electron volts, and the mass of a proton times c squared is about 1 billion electron volts, so a 2 billion electron volt photon has enough energy to produce a 1 billion electron volt proton and a 1 billion electron volt antiproton. Photons can go to proton-antiproton pairs, proton-antiproton pairs go to photons. 1 microsecond after the Big Bang, the temperature was 20 trillion Kelvin, and the proton-antiproton and neutron-antineutron pairs were generated in great abundance. Now, since photons produce a particle for every antiparticle and an antiparticle for every particle, particles and their antiparticles combine to produce photons, it's not clear why there's any matter left in the universe today at all, since all the matter and the antimatter should have combined and annihilated, leaving only photons. Then, when the space-time expanded enough so those photons could no longer produce particles and antiparticles, the universe should have been empty. It should have been photons alone. Prior to 1 microsecond, the density was more than 1 billion tons per teaspoonful. That's the density, you may recall, of a neutron star, which is equivalent to the density of nuclear matter. The entire universe was a giant atomic nucleus. And this meant the protons and the neutrons were squeezed so close together they were effectively touching, as they do in a nucleus, overlapping with each other and dissolving into their constituent quarks. Somehow, at this time, at this critical transition, where protons and neutrons solidified from the quark soup and became distinct entities which would then carry forward to the universe today, a slight asymmetry left us with 1,000,000,001 protons for every billion antiprotons, and for 1,000,000,001 neutrons for every billion antineutrons. The matter-antimatter pairs annihilated, producing 1 billion photons, so that for every billion of the antimatter and matter pairs, only a single proton and neutron were left. These lonely remnants comprise all of the matter in the universe today. Perhaps the Large Hadron Collider, soon to come online in Switzerland, will give us a hint as to why this asymmetry occurred. Whatever it was, we wouldn't be here without it. The quark era, before 1 microsecond, remains the subject of much speculation. But the story from that moment to today is pretty clear, and our history of atoms is now complete. This was the goal we set at the outset, to construct all of history from the first microsecond of the universe to today. We've used all the actors of the microworld in this process, protons, and neutrons, to form the isotope that mark chemical and geological processes, electrons jumping in their orbits to identify these isotopes, and photons to signal their presence across the universe, and even to see the atoms form in the background radiation. Positrons to signal radioactive decay, neutrinos to peer into the core of the sun, and quarks to provide the yet hidden asymmetry that allows matter to exist in the universe today. This is the story as told backwards in time, but we're used, of course, to time running forwards. So let me review our microcosmical history by following a single up quark from its birth just before the first microsecond barrier. At t equals 1 microsecond, our up joins another up and a down quark to form an unbreakable bond and become the universe's first proton. At t equals 10 to the minus 4 seconds, it bumps into a frisky electron and joins with it to become a neutron, canceling out its positive charge. At t equals 10 seconds, bored in this neutral state, it spits out the electron to become a proton again. But within seconds, it bumps into a neutron and becomes a deuterium nucleus. A few seconds later, however, a photon comes along, splitting up that deuterium and knocking our proton back to its lonely state. A minute later, our proton finds another neutron companion, and this time the relationship lasts, since no photons remain that are powerful enough to tear it asunder. Within seconds, it encounters another deuterium and quickly forms a nuclear family of 4, a helium nucleus. Hundreds of thousands of years go by, but the helium nucleus remains positive. By then, life has slowed down sufficiently that a couple of electrons wander by and are captured into orbits around the nucleus. The universe's first atom is complete. Occasionally, a passing photon will eject one of the electrons, but since all electrons are identical, a new one quickly replaces it, and no one is the wiser. Content now with its 2 electrons, unwilling, indeed unable, to form bonds with other atoms, our helium friend drifts around in an ever-expanding universe. After a billion years or 2, however, it finds itself in an unusually dense part of space, and it's gravitationally drawn towards trillions of its brethren, or to be more precise, 10 to the 68 other protons and helium nuclei, most of which are hydrogen cousins, to help construct a galaxy, our Milky Way. Visits to other atoms now require a trip of only a centimeter or so. Helium is part of an interstellar gas cloud. 7.5 billion years pass, and it feels the neighborhood suddenly getting crowded, with more than 1 million of its fellow atoms stuffed into a formerly isolated 1 cubic centimeter of space. Things continue to get worse. Soon there are trillions of neighbors. Its electrons get stripped for good, and it's back to its primal, positively charged state. After 10 million years of constant jostling and ever harsher conditions in the core of a massive star, it finds itself confronted, simultaneously, with 2 identical companions. And in an instant, they snap together and form a lifelong bond. A carbon nucleus is born. A few 100,000 years later, carbon finds itself thrust out of its steamy environment at nearly 1/10 the speed of light by the explosive destruction of the star that made it. And soon, our Mr. Carbon is in much less crowded circumstances. 1 million years on, in frigid surroundings now, it bumps into a solid surface and it sticks. On this cold little interstellar dust grain, there's a party. 5 other carbons, 2 nitrogens, 2 oxygens, and 14 hydrogens are invited. They are so attracted to each other, they make some bonds, in a left-handed sort of way at least, and form a lysine molecule, an amino acid. 12 million years later, the group lands with a thud on a kilometer-wide asteroid, where they chill out for a while. Then, after several million more years pass, their temporary home falls hard, bang, onto the crust of the newly formed Earth. Things gradually settle down, cool off a little bit for our quark in the proton, in the carbon nucleus, in the lysine molecule, until one day, a few 100 million years later, our lysine finds itself floating in a pool of water. Eventually, a triplet of adenine molecules wanders by and, spying a lysine, grabs on tight. It soon finds itself unceremoniously glued to a whole bunch of neighboring cousins, amino acids all, making up a simple protein. Now the fun begins. From the comfort of an archaeobacterial cell wall to the sludge at the bottom of a pond, from the gut of a worm to the yolk of a bird's egg, 4 billion years of constant transformation passes by. Often, our carbon atom breaks free from its companions. It spent millions of years alone, locked in the calcium carbonate of a foraminifera shell 3 miles under the sea. Once it found itself shot out of the crater of a volcano, linked with 2 oxygens, but otherwise free to roam the Earth. For 400 millennia, it was trapped in a tiny air bubble in Greenland's glacier, liberated into a warm lab at last by a curious man with a needle. It escaped out the window from the lab, but was soon captured by a tree leaf and linked again with dozens of its companions into a molecule of cellulose. Rousted out of a comfortable ring in the tree by a man with a little borer and dropped unceremoniously onto the ground in a speck of sawdust, it was accidentally ingested by a passing pheasant pecking at the ground for seeds. But its home in the pheasant's breast would also be short-lived, because I roasted that pheasant and ate it last week. And now, Here it comes. That original quark in our proton, in our carbon nucleus, now joined with two oxygen friends, finds freedom again. There it goes. That quark has been on a journey for nearly 14 billion years. Science has been on its journey to discover this tale for a mere 400. Galileo knew nothing of atoms, but in 1609, his telescope gave us new worlds to think about. More importantly, Galileo gave us a new approach to the universe. The notion that it is a great book, written in the language of mathematics, as he said, and that we can understand this book if we learn that language. In short, that the universe, the unity of the diverse, is comprehensible. In that spirit, we have applied physics to matters art historical and archaeological, chemical, geological, and astronomical, in order to enrich and extend our view of history. A few topics have practical applications. The use of isotopes in medical diagnostics, and the importance of past climate change to future climate prediction touch on two of the most important topics of our age. Others, knowing when Native Americans learned to plant corn or how the carbon in your fingernail was cooked up inside a star, will affect neither your longevity nor your brokerage account. Nonetheless, it is my hope that these tales of atomic detection work have enhanced your appreciation both of history and of science, and have expanded your perspective on your place in the universe.